No one, but it's a thing still.
Oh, small person.
Check. Wait for Christian maybe. Christian, you okay?
Oh yeah. I just didn't. My class in the afternoon got canceled, and I was working on the house, and it got a little bit late, and so I decided it'd be easier to just stay here and do class today, than try to make the drive. So sorry I won't be there, but I'll be on this side.
Yeah. We postpone the homework 6 a little bit. Well, we made it due on Wednesday. And we have midterm 2. October. 9. So are others there? No. Okay. Okay. We did a non-trivial example of the electric field due to a charged sphere, starting from the electric potential. Basically, the electric potential due to a charged sphere that comes out really nice using these methods. We want to do the electric potential due to an electric dipole this time, and preferably even talk about what is a point dipole, and that is what we want to go into in the next week. So idea here is again electrostatics. So electrostatics. Strategy we are saying, or the equations first of all is that the divergence of the electric field is equal to charge density over the permittivity of vacuum, and del cross the curl of the electric field is equal to 0, which immediately implies that electric field is equal to negative gradient of phi. This is very similar to what we talked about in conservative forces. If there's a conservative force, then there is a potential energy. Here, if curl of electric field is 0, then we say that electric field can be written in terms of the divergence of an electric potential. And this immediately, if you put it back in here, then you get the Laplacian of the electric potential has to be rho over epsilon naught. So that's our solution if you want. And we suggested that whenever we have a description, try to get the charge density first. So charge density and the mathematical the mathematical description of a charge density. Then immediately get the electric potential as an integral, basically the superposition principle that we encounter in elementary physics. And this is the integral form of that superposition principle. So this is charge. Notice R prime is integrated over 1 over R, Q over, remember for a point charge we have 1 over 4 pi epsilon naught, Q over R to be your electric potential. There could be a lot of charges. This sets the position of the charge R prime, and you sum over the position of the charges, and you get the electric potential due to a distribution of charges. Right. That's your process. And third is you get the electric field. Once you complete these integrals, you take the gradient of this expression and you get the electric field. Notice you can in fact directly do this gradient inside of this integral. You could take this gradient operator inside because this integral is with respect to R prime, and the gradient of 1 over R is the expression for the electric field due to a point charge. So electric field also satisfies the superposition principle. You can either add up the potential, first do the potential and then take the derivative, or take the derivative and then calculate the potential, either way. And today we want to talk about the electric potential in this manner of an electric dipole. So this is an electric dipole. It's often called electric dipole moment also. And what we're saying is that there is a point charge say this is negative and that is a positive point charge. Both are of charge Q, so this is minus Q and that's plus Q. We have a choice that this could have been minus Q1 and that could have been plus Q2, or for that matter, even if, as we will see in the next couple of lectures, we will define a more general dipole moment for any 2-point charges, or for that matter, for given any distribution, we will be able to define an electric dipole moment. But for now, this is minus Q and plus Q separated by a distance A. And let's choose this to be on the x-axis. Let's choose this to be, or did I say, like I think in your homework, this is along the z-axis. So let's say this is z-axis. And this could be your origin. So this sets the position of the charges. So let's say the position of this charge is x is 0, y is 0, and z is plus a. And here it is 0, 0, and minus a. So the distance between them is 2 times a, and the dipole moment is defined as electric dipole moment P. Electric dipole moment of this configuration is defined as the distance, the vector connecting minus charge and the positive charge. So it goes from the negative charge to the positive charge. That's your vector, and multiply by the charge. So it is Q times 2 times A in the z hat direction. Notice it's a vector, and its magnitude is given by the charge times the distance between. So that's your dipole. There is a finite distance between them, and immediately we can define something of an extreme limit of this, and think of what is a point electric dipole. And what is that? What we want to do is take the limit 2 times A going to 0. So that means to say the distance between the charges is 0. And that means to say the charge plus Q and minus Q comes together. But you want to set Q tends to infinity. So this is 0, but that's infinity. That means to say 1 over 0, but in such a way that 2 times A times Q, which is actually our magnitude of P, this remains fixed. This is 0, that's infinity, but this multiplication, that doesn't go to 0 or infinity, so that stays fixed. So that means to say that these two, one is small and one is large, that exactly cancels out. So this is an extreme limit, and that's what a point electric dipole is, right? You have two charges right on top of each other, but they have a finite, there's a direction associated with it. So that will be our point electric dipole, and this will be the approximation we typically work with atoms. Like when we think of an atom, it is actually neutral, right? There is no charge on it. There is no it's considered neutral, but the charges might be distributed in such a way that it is slightly oriented in one direction. All the positive charges might be on one side, and all the negative charges might be on the other side. So the property of an atom with which we can really electrically align or assign is a point electric dipole. If it is charged, then it is not really an atom, and it's an ion. Ion has some characteristics, but atom, if you want to describe an atom, do two atoms interact with each other, both are neutral, they could if each of them have a dipole moment. And that's what we would like to eventually work with. But as of now, this is just the point electric dipole. So let's go back. So this is a point electric dipole. This is a standard electric dipole. We will start with this, and somewhere at some stage, we will take the limit of that becoming a point electric dipole. So what's the charge density of a dipole? So this is a dipole, simple dipole, not a point dipole. There are two charges, so we just have to add the two charge distribution. If it was a point charge, we simply say it is the delta function at one point. So that's the position of the charge minus where is its state situated. So this is a positive charge we are talking about. So it is situated at plus AZ. So it is A times Z hat. So that's the position of the charge. And there is another charge which is negatively charged, and that is placed at R minus of minus AZ hat, which will make it plus AZ hat. Right? Its position is minus AZ hat. So that will make it plus. This is a short version of the following expression. So this is Q times delta of X, which is 0, X minus 0, delta of Y minus 0, and delta of Z minus A. these are the three coordinates of x, y, z, the position. It says that x minus 0, y. So you don't have to write 0, delta of x, delta of y, and delta of z minus a. And the second charge is at similarly x, delta of y, and delta of z plus a. That's pretty much what your charge density is. If we substitute this in here, we should get the electric potential due to a dipole. If you have a dipole, what's your electric potential? Remember that this is like a magnet, so these field lines will start from the positive charge and go into the negative charge. So the field lines, the electric field lines for this look something like that. That's your magnetic field. So they start from the positive charge, go into the electric. That's how the magnetic field you do it. A magnet looks like. So this is an electric version of a magnet. In a magnetic field, we don't talk about a point charge because magnetic monopole doesn't exist. So let's calculate the electric potential for this. Phi of r is equal to 1 over 4 pi epsilon naught. Integrate over all the sources. There are two sources here, 2 point charges, and this is rho of r prime over r minus r prime. Let's explicitly write this just so that we have a clear picture of what we are doing. So this is 1 over 4 pi epsilon naught. This is integral over z prime of the primed variables, y prime and z prime. And the charge density is q times delta of x prime, delta of y prime, and delta of z prime minus a plus, minus, right? Minus of delta of x prime, delta of y prime, and delta of z prime plus a divided by the distance between them is x minus x prime square plus y minus y prime square plus z minus. That's pretty much what we do in other cases or in elementary introductory physics courses also. It's just we are explicitly writing the form for the charge density and letting the integrals bring out the electric potential instead of directly writing the electric potential. It's sort of mechanical stage, but in a more elaborate form, this is more useful. These are two terms, so let's do that two terms separately. But each of the terms, all the three integrals can be done because a delta function integral pretty much asks you to replace x prime with 0 here, y prime with 0, and z prime with a. So this is q over 4 pi epsilon naught. So that's your first expression. So the first integral I'm doing, which is set x prime is equal to 0. So this is x squared plus y squared. When I set x prime is 0, y prime is 0, and z prime is z minus a squared. And the second one is q over 4 pi epsilon naught times 1 over same thing plus z plus a the whole square. You could have arrived at this step right from the beginning if you know that the electric potential due to a point charge is Q over R, where this is the distance between them. So this is the potential due to the positive charge. This is the electric potential due to the negative charge. So it is just an elaborate way of reaching at the same result. But the advantage of this is that now this is valid for any charge density, like even if it's not a point charge. Okay, so that's good enough. But now we want to make this approximation that A is actually small. So let's go for the approximation that our observation point, which is really far away, is much larger than the distance between the two charges. So so these are the kind of approximations we will work with. So let the distance A be very much less than magnitude of x, magnitude of y, and magnitude of z. Right, that's what we want to work with. So again, the diagram here is that this is your z-axis. So that's your positive charge, that's your negative charge. And there is an observation point here. So this is your R, which is x, y, z. And observation point is really far compared to this distance. This distance is Q times A. That's an approximation we are talking. And by how much large? If it is 10 times large, that means that's 10% accuracy. If it is 100 times large, that's 1% accuracy, and so on. So very broadly speaking, that's the kind of approximation we are talking. If that is a case, we can write our expression here as x squared plus y squared. Let me write this for the electric potential itself. This is x, y, z, if you want. X, y, z. That's the same as writing R. And here we have Q over 4 pi epsilon naught. And 1 over, expand this out. So this is x squared plus y squared plus z squared. And I have minus 2 ZA. And then there is a plus A squared. And that is a square root. Same thing on the other term. I would like to neglect this A squared. So the leading, if A is large, maybe do this in 2 steps, that will come out better. So this is Q over 4 pi epsilon naught. Take the x squared over y squared outside, which is nothing but the distance between. So this is this distance, right? R. That's that magnitude of R. And this is 1 minus 2 times Z times A over, when I divide this out, that is R squared plus A squared over R squared. Minus Q over 4 pi epsilon naught. Again, this is 1 over R. So it's the same 1 over R here. And I pull that out, 1 over 1 plus QZ A over R squared plus A squared over R squared. We really want to take the limit A tends to really small. We can think of it as going A tends to 0, but better, this is very small compared to that. In that case, this term can be neglected. Like for example, this was 0.1, this is 0.01, so that's the form of approximation here. Talking about, so this term also goes away. I have an expansion, I have an expression which is 1 minus a small quantity. So let's figure out what is 1 minus x. If x was small, this is very much less than 1. This has a series expansion. So this is, think of a binomial series expansion. You do 1, that is a, so this, how you will do this is 1 minus x raised to minus half. Right? That's how this is. What is the expansion for this? You would say it is 1 plus, write the power first, so that's minus half. And then whatever is inside, so this is minus x. Next one would be higher orders. The general expression for this is 1 plus x raised to n is equal to 1 plus n times x plus n times n minus 1 raised to 2 factorial times x squared, and it keeps going. So n into n minus 1 into n minus 2 over 3 factorial times x cubed, and so on. So in general, you can expand anything, but we are interested just in the leading order. So it is 1 plus x over 2 and higher terms. We have already neglected a square term, so there is no point in keeping the square. Yes.
Do you neglect those terms because they're insignificant?
Yes, insignificant. So for example, if a over r was equal to 0.1, then a over r squared is 0.01, and that is already a 1. So if I'm doing 1 plus a over r plus a over r squared, then it is 1 plus 0.1 plus 0.01. Right? So this will be 1.11 in a sense. So, so if I am working with 10% accuracy, I can kill this. So that's the kind of expression we are talking about. But this is much more than that. Think of this to being an atom. Like an atom, and you're observing in a lab, let us say, even if it was a micrometer sized quantity, this is a over r is about 10 raised to minus 6 or something. And a over r squared then immediately becomes 10 raised to minus 12. So that's really insignificant. So it's because this is practically 0 for what we're talking about. So even though it seems like it's an approximation, it's an approximation that we never have to worry about unless you're doing extremely precise experiments, or you have detail, you want details to that extreme, the leading order terms. Okay. So with that idea in mind, so I want to invert that. So that's 1 plus, and 1 plus will become 1 minus. Right? So let's write that down. So it is q over 4 pi epsilon naught. This is 1 over r. And this expansion we said is 1 plus this time. It is plus 2 times z a over r squared. And there are higher order terms if you want. Same thing here, q over 4 pi epsilon naught, 1 over r, and this is 1 minus this time q z a over r squared. Notice when I add these two quantities, this cancels out. So the leading order cancels out. That is a neutral quantity, right? This is the electric potential at this point due to the positive charge. This is the electric potential due to the point at this observation point due to the negative charge. But these are so close that they balance each other, right? That's that cancellation. But there's a small deviation. That's the first leading contribution from that deviation. That's what that means, and that's all we want. And now, but these two don't cancel, right? This is minus and a minus adds up. So this leads to Q over 4 pi epsilon naught 1 over R, and you have 4 times, so that's R cube, right? And that is 4 times A times C. That's your expression. And so this is plus order A over R squared. We have neglected that quantity. And if, since that is there, technically it's kind of. So that's your electric potential. So this will be considered electric potential due to a point dipole. So since we made this approximation, so this is the same as electric potential due to a point dipole. But let's rewrite this in a certain form so that we can use this in a more generic way. So electric potential phi R is equal to 1 over 4 pi epsilon naught. And let's introduce our P. So remember, your P was Q times A times Z. For a point charge or for a point electric dipole, it is now the charge and the distance that is important. Is 2 times A times, sorry, what did I write? Not Z, right? 2 times A times Q. That's your magnitude. And it has a Z direction also, right? If I were thinking about the magnitude, it is 2 times A times Q times Z hat. So we want to keep that also in mind. And in that way, I can say this is 2 times P times Z over RQ. That's good, but we can write this in the following form. So notice Z in spherical coordinates is nothing but R cosine theta. Remember, your R hat or vector R is R sine theta cosine phi in the I direction plus R sine theta sine phi in the J hat direction plus R cosine theta in the K hat direction. So vector R dotted with K hat would be equal to R cosine theta, which is exactly your Z component, right? That's why Z. If I were to write that in that form, I get phi epsilon naught times I made a mistake here, right? Yeah, I made a mistake here. Sorry. I said that my expansion was 1 minus x is equal to 1 plus x over 2 plus so on. Right? That was what I said. But then I forgot to write my 2 there, 1 over 2. So this was my x itself. So there is a factor of half that should have been here. Right, is that clear? Any confusion, sir? Okay, please correct on that. So this is 1/2 in here.
Final answer is 2AZ.
Exactly. It's not 4AZ, it is 2AZ. So there's an extra 2 that is showing up there. I should have caught that before. 2AZ. And this becomes simply P times Z. And this is P times cosine theta, then the R cancels out. And this is R squared. So electric potential for a point charge goes like 1/R, but the electric potential due to a point dipole goes like 1/R squared. In fact, this can be nicely written as 1/4 pi epsilon naught P dotted with R divided by R cubed. And then what I've done with that is that we had earlier chosen the direction of the dipole to be along the z-axis, but now there is no restriction. So this is a much more general expression. So that's your electric potential due to a point electric dipole. So by point electric dipole, what I mean is, so this could be anywhere like, so we have axis and this is your P. It only has a direction, it has no structure. Think of a really small atom, but it is an oriented atom in the sense all the charges are more dominantly distributed on one side of the atom than on the other side. But they are so small that it's only the direction that is picked out. Rest everything has no content in them. There is no structure as far as volume goes, but it still has a direction. That's how you want to interpret an electric point electric dipole. That's good. And very broadly speaking, that's like a magnet. Right? A magnet is also like that. It has an orientation north and south. Right here, it is positive and negative charge. So, what is the electric field associated with this point dipole? That's negative gradient of the potential energy. So, if I take the gradient of that, I should get that. So, let's see how we do that. So, we have negative gradient of 4 pi epsilon naught, and I have to gradient, and let me write this as R dotted with P, so that this is R dotted with P over R cubed. And this is where we can use our vector calculus that we studied earlier. Notice this gradient has to act on this vector R, which is having position dependence, and this magnitude of R in the denominator. It has to do both, and that is 2 terms. So when this hits on the numerator, this is a dyadic, right? P. P is uniform, that's a constant, it doesn't depend on position, right? So to clarify that this acts only on this R, I write those brackets, and that's 1/R cubed. Right? This is acting. And there is another term, which is plus gradient acts only on this. Gradient acts only on R cubed. That is R dotted with A stays as it is. Notice how the operations are working. Remember your vector calculus that we did in the first few weeks. And I said the summary is that the most important identities we will need is that this dyadic quantity, when the gradient and the position vector comes together, that's actually a unit dyadic. Right? And when the gradient operator acts on the magnitude of R, this is actually R hat. That's the quantities we need. Minus 1 over 4 pi epsilon naught. That's a 1 dotted with P. Any identity matrix or identity dyadic acting on a vector gives you back the vector itself. So straightforward. Cube. Here, this is minus 3 over R raised to 4. So it's a chain rule now we're doing, times the gradient of R. First, do the differentiation as if it was a normal function, and then finally use the fact that I have to use the chain rule, so I have to take the gradient of the magnitude of R, which we know is R hat. Going slowly, like writing more steps. 4 pi epsilon naught, and this is P over R cube, and this is minus 3. This is R hat, and that is vector R dotted with P over R raised to 4. But I can get rid of one of the R's by making this a R hat, and that's what I'll do, and I'll rewrite this without the sign. And right, this is 1 over 4 pi epsilon naught, 1 over R cube, and write this in the front. That is 3 R hat dotted with P minus of the P vector itself. This is actually how a magnetic field due to a magnet also looks like. This electric dipole is pretty much the electric analog of a magnet that we come across. And if you notice, we often do not, we never say what is the magnetic field due to a magnet, right? We work with the magnet a lot in the introductory physics courses, but we never write it down because it has a slightly more complicated form than a point charge. Okay, so that's your electric field. Can we plot this or have a feel for it? So, let's have, this is our electric field, right? Electric field for any observation point, R could be anywhere, is given by a point dipole is 1 over R cube, 3 R hat dot with P minus of P. So let's consider a special scenario. So let's say that's your Z axis. That's your origin, and let's say the electric dipole is actually sitting here. That's your that's origin, and that's your P. Right. So let P be equal to P times Z hat. So it's in the Z hat direction. And that's first case. Let's ask. What is the magnetic field or the electric field actually now? Somewhere at a certain distance on the z-axis. Right. So let R be equal to, so the observation point is somewhere here, so that's a positive distance. So it is z times, let's say it is k hat, right? I write z hat sometimes, so that's a z times k. So R hat, so that means that R hat is equal to k hat itself. And what is your electric field? Electric field is 1 over 4 pi epsilon naught. What's the distance between that? If we say r is z times k, magnitude of r is z itself. So it is 1 over z cube. Z we are saying is positive, and this is 3 times r hat is k hat. R dotted with p is equal to p times z hat, right? So r hat dotted with p will be equal to, this is z hat itself, so it's just p. So it's just p minus of p times k hat. So they don't cancel each other. So it is 3 times p minus p, so it is 2. Factor of 2 remains. So it is 1 over 4 pi epsilon naught times 2 times p over z cube times k hat. So it's not 0, so this points in this direction. So the electric field everywhere here is in this direction. That's how the electric field is coming out. Let's go now below this charge on the z-axis itself. So let's do the second point. Let's say r is equal to minus z times k hat. So with this being magnitude, right? Let's say that's a positive quantity, but somewhere down here. So the electric field now is 1 over 4 pi epsilon naught. It is r cube, it is a distance cube, so it is 1 over z cube, magnitude z cube. And we again have to do 3 times r hat now. So notice what is going on. So here r hat is minus, right? So it is minus z hat. And that is a k hat. No, r hat is still, r hat is equal to minus k hat. With no z hat. This is minus k hat. R dotted with p. So p is here, r hat is minus, so it is again a minus k hat. So minus 1, minus p. So instead of plus p, this becomes minus p. So r hat dotted with p is equal to minus p. Be careful with how you see that, and minus of p again is the same, so it is p times k hat. If you notice, again this is plus 3 times p minus p, it's exactly the same in the same direction. So this is 1 over 4 pi epsilon naught times 2 times p over magnitude of c cube times k hat. So it is still in the same direction. This has to do with the fact that for a magnet, this magnetic electric field is like this. This is how the magnetic field looks like, or electric field of that point. Dipole, it comes back and again it orients itself along the z-axis in the upward direction. What about somewhere here? What if you were somewhere on the x-axis? Apparently it is pointing downward. So let's do a third scenario. Let's say r is equal to, this time it's along the x-axis, let's say. So it is x times in the I direction. We do the minus I also. So r hat is equal to I hat, and we have r hat dotted with p. What is r hat dotted with p? This is I hat, and p is p times k hat. But I and k is 0, right? So this is equal to 0. Right? So the first term go to 0 now. So the electric field is equal to 1 over 4 pi epsilon naught. Distance is 1 over x cubed. And this is 0 now, minus p times k hat. So it's surely weaker. And in the negative direction, so this is equal to minus p over x cubed. So instead of having a factor of 2 if x and z were the same, this is weaker. At the same distance, if you go here, this is actually weaker. Usually you see this by the intensity of this lines, and it's also pointing downward. In general, you should be able to find the magnetic field at any point, right? It will be always tangent to this line. This is electric field. I keep saying magnetic field because it looks like a magnet. Actually, a magnet has exactly the same expression as we wrote for an electric dipole. This shows up in your homework. I pretty much worked this out, but I think this is a very important example. So nothing wrong in repeating. So I'll stop here. Thank you.
Thank you.
Our next test